All right, hello everybody. Uh, Grab your model. This is the time where this is going to become a three-dimensional model instead of a piece of paper. What we're going to do is we're going to take this piece of paper and fold it up so the bottom of the piece of paper comes up to this line like this. Okay, and fold that over real nice. Fold that over, and then like that, so the edge of the paper meets up with that thin line, and then fold this over. You're doing this, right? You're not just making fun of my receding hairline, I hope. And you should have something that looks like that. It kind of looks like a piece of paper folded in half. But the idea now is you should be able to see very faintly through the paper vectors W and U. What I want you to do is trace over them, so now you'll actually have a model of vectors in three-dimensional space. I'm going to do that. You do that too. I'm not, I'm just pausing the video for a second so I can do that. Okay, you should have something that looks like that, where now we've got three vectors in three-dimensional space, and not only are these not collinear vectors, but the three vectors are on different planes, aren't they? Right? So one shooting off in one direction, these two are on this plane, but U is on a different plane. And so, it's a different case than this case here where we're worried about whether they're parallel or not. These three vectors aren't even on the same plane anymore. And that's kind of an important thing. We're going to get back to the diagram in just a second again. So I'm going to go back to the note here, and we're going to start talking about three dimensions. So spanning sets in three dimensions. We define the standard basis vectors for R3 as I, J, and K, again, unit vectors in the direction of the x-axis, y-axis, and z-axis. And these vectors form a spanning set for R3, since any vector U, which is ABC, can be written as a linear combination of these three. Because it was easy then, we just sort of picked out the coordinates, and we could say that U was equal to AI plus BJ plus CK, where these I, J, and K were unit vectors in the direction of the X, Y, and Z axis. So if I had my picture here, back to the picture, then the X axis is the one pointing this way. So I could write, and I will in a moment, I could write I as a little vector in this direction. J would be in the direction of Y, which is this way, right? X and Y. And then K is in the Z direction, would be a little vector here. So I'm actually going to add I, J, and K, and then we could see any vector U that was shooting off into space, anywhere like this, could be just some linear combination of I, J, and K. All right, I'm going to pause the video and put I, J, and K on my three-dimensional model. All right, so just like I promised, we got I in the direction of the x-axis. We've got J in the direction of the y-axis, which is pointing straight out at you, and K is in the direction of the z-axis. And any old vector in space can be written as a linear combination of these three. That's no problem. We've seen that before. But just like we said that U and V were a basis for the plane rather than just I and J, is it possible that the three vectors that we see in three dimensions here, U, V, and W, are a spanning set for space? And indeed it is. That is possible. Now, it's not that they can't be parallel, like in the sense in two dimensions. What has to be true for them to be a spanning set in three dimensions? Well, they can't all be on the same plane. So if I folded it flat and I was talking about U, V, and W, I couldn't say that those three were a basis for space because I couldn't get off this page. U, V, and W were all on this plane, and I couldn't get off that page into space. So I would need a third vector that's on a different plane as the first two. In this case, now, because I folded the model, I have U, V, and W all not on the same plane, not coplanar. That's the idea. And so down here, we're going to write some stuff about what it means for three vectors to be a basis for space, or for a spanning set for space. And so right here, we are going to write this stuff. Are you set? In R3, the following can be stated about vectors U, V, and W. This is with your folded model. They're not coplanar, which means they don't lie all on one plane. We can say all vectors in R3 can be written as a linear combination of these three, i.e., that is, for any old vector z, we can write AU plus BV plus CW. That means these three vectors are a basis for space. We also say, because we can do this, that U, V, and W are a spanning set for R3. We also say that U, V, and W are a basis for space, R3 space, right? We also say that the three vectors are linearly independent. Also, this means that if I took one of them, I couldn't write the other two as a linear combination of the other two. So you can't, and this is all of the above things all mean this, but here's almost like a side effect, a consequence. You can't write one as a linear combination of the other two. That's almost like a side effect. Okay, I'm going to pause there. We're going to come back for, I think, video 4. We might even have 4 or 5, but they're reasonably short, and this is involved stuff. We're going to use our stick-it notes, and I'll show you how we're going to use our stick-it notes in a second.